Hello guys, today we will be talking about the applications of power series. So, firstly we will talk about Taylor and Maclaurin series, and later we will be discussing approximating functions by polynomials, right? So as we discussed in our last lecture about power series, right? And we know that the power series are in form of sigma c sub n into x power n, where our n is equal to 0 and goes to infinity, right? So that's all about the power series. But we also know that the sum of power series is, or it can be represented, right, in the form of function. So we'll expand the understanding about this kind of series where we have f of x is equal to c0 plus c1 into x minus a, right, plus c2 into x minus a square. So what do we have? We have minus a additionally over here, right, as compared to power series. So now it won't be really tricky to solve this kind of series because we will be just substituting our a with x, right? And then we'll be able to solve that. To begin, notice if we put x is equal to 0 in our equation 1, then all terms after the first one are 0, right? Because when we, when substitute a with x, our a minus a would be equal to 0, right? So this binomial will be automatically equals to 0. And here we have this c2, right? Again, we'll just replace our x with a and it will become 0 over here. So this binomial will be equal to 0, and that will make this coefficient also equal to 0, right? So we will only having one value which will be equal to c0. Okay, now we're just going towards the differentiation, and when differentiation comes to play, we know that our f prime of x would be equal to c1 when we will be substituting our x is equal to a, right? Because it's the same thing. We will just differentiate the whole series over here, and then we will substitute x with a and it will become 0. These binomials will be becoming 0, right? And these binomials will make our coefficients equal to 0 as well, right? So our f prime of a would be equal to c1. Now going to the third one, we see that we have to find the double prime of x, right? It means the double differentiation. All right, so what do we find over here? We see that our f double prime of a is equal to 2c2, right? Why? Because again, we are just having the differentiation. We are having the double differentiation, or double prime of x. And then we will be just putting our x is equal to a, right? And that will become 0, and it will make our coefficients equal to 0, right? So after that, we have the f triple prime of x, right? Which is equal to 2 into 3c3 plus 2 into 2 into 4c4, right? So all this thing would be equal to, so right, if we substitute our x is equal to a again, so what do? We have f triple prime of a is equal to 2 into 3c3, and it will be equal to 3 factorial c3, right? And we know that what we have done with this thing, we have just substituted our x with a, right, in equation 4 as well. So when we continue to do this kind of thing and we see the pattern over here, right, we see the pattern, and it will becoming f n prime of a is equal to 2 into 3 into 4, and it will be going toward n c sub n, right? And it will be equal to n factorial c sub n, right? Because we know that we'll keep adding we'll keep doing the differentiation, right? And in order to achieve our last possible differentiation, it would be n factorial c sub n, right? Now we can therefore set up an expression to find the nth coefficient of the series, right? So here we have c sub n is equal to f of n, or f prime n into a, or f prime n of a, right? It is a bit tricky to just speak about this kind of differentiation, but we know that it will be having the n factorial as a denominator over here. So the formula remains valid, you know. It if our value, if our n is equal to 0 as well, still the formula is valid, because we know that our 0 factorial is equal to a. And if we have f prime 0, you know, f of there is no such kind of differentiation for f, it will be simple f, right? So thus we have proved the following theorem. So to summarize, for the function given by the sum of c sub n into x minus power n, right, where the absolute value of x minus a is less than r. So it means that what is r? R is the radius of convergence for the series over here. So the coefficients of the functions are given by this formula. C sub n is equal to f n prime a of a divided by the n factorial, right? So we can just simply say that we will be switching this thing, we will writing this particular so substituting this formula for c sub n back into the series, we can see that it is a power expansion at a, it must be in the following form, right? So we're gonna write it f of x is equal to sigma f n of n prime of a divided by n factorial into x minus a power n, right? And our n is equal to 0 and goes towards infinity. So we will just simply writing down in this form of series f of a plus f prime of a divided by 1 factorial into x minus a plus f double prime of a divided by 2 factorial into x minus a square plus f triple prime of a divided by 3 factorial into x minus a cube, plus it will be just going towards infinity, right? So we can say that this series in equation 6 is called Taylor series of function f at a, or function f about a, or centered at a, right? So if we then generate a new function of same form, right? All right. We can say that since we understand the Taylor series, let's talk about a special case over here where the value of a is equal to 0, right? So the binomials will be simply f of x is equal to sigma f n prime of a 0 into n factorial, right? And it will be multiplied with x power n. Right, we will not write x minus a power n because we already know that a is equal to 0, right? So it has no impact in this particular equation. So when we simplify it, it would be in form of f of 0 plus f prime of 0 divided by 1 factorial into x plus f double prime of 0 divided by 2 factorial into x squared and up to infinity. So this case arises frequently enough, and it is given by the special name Maclaurin series, right? So you know, every time we have a, we will just simply write down 0. So this kind of special case is also known as Maclaurin series, and this Taylor series with expansion about the point where x is equal to 0. All right, now in the case of Taylor series, the partial sums we have, they are t sub n into t sub n of x is equal to sigma f I prime of a divided by I factorial, right? And it will be multiplied with x minus a power I, because we have this, and its I is equal to 0, right? We have this I over here, it's equal to 0, and it will be just going to, and we know that we have a specific number over here. It could be 6, it could be 7, it could be 8, and our n could be any number over here, right? So what do we do when we simplify it? It would be f of a plus f prime of a divided by 1 factorial into x minus a, right? Same form, we just writing it down, and we'll be adding this series. So t sub n is a polynomial of degree n called nth degree of polynomial, a Taylor polynomial of f at a, right? So we know that this is actually particular, it is actually a partial sum, right? So there would be a particular stop. We know that there would be some sort of value for n, understand? Okay, for instance, for the exponential function f of x is equal to e power x, the result of example 1 shows that the Taylor polynomials at 0 with n is equal to 1, 2, and 3 are such like t1 of x is equal to 1 plus x, t2 of x is equal to 1 plus x squared divided by 2 factorial, t3 of x is equal to 1 plus x squared by 2 factorial plus x cubed by 3 factorials. And we are not just heading towards the infinity because these are the partial sums, right? And we have our n is defined over here, you know, our n would be equal to, our n would be stopping at 3, right? So the graph of the exponential function and these Taylor polynomials are drawn in the figure. Oh, okay, now we can see in the figure 1, right? And we can see that we have this is actually y is equal to t1 of x over here, this particular line, right? And when we see the t2 of x over here, it is actually a parabola, right? And when we see t3 of x, it is this blue, it's a blue curve over here, right? And then we have y is equal to e of x, right? So as n increases, t sub n of x appears to approach e power x in figure 1. So this is just that our e power x is equal to the sum of its Taylor series, right? So guys, in general, f of x is sum of its Taylor series. You know, if f of x is equal to limit t sub n of x where n approaches to infinity, right? And if we let r sub n of x is equal to f of x minus t sub n of x, so that our f of x would be equal to t sub n of x plus r sub n of x. Now here our r sub n of x is called remainder, you know, this thing would be remainder of the Taylor series. And we can somehow show that the limit r sub n of x where n approaches to infinity is equal to 0, then it follows that limit t sub n of x is equal to limit f of x minus r sub n of x is equal to f of x minus limit r sub n of x is equal to f of x. So it seems that it's equal to f of x, and it would be remainder of the Taylor. So we have therefore proved the following: if f of x is equal to t sub n of x plus r sub n of x, right, where tn is actually the nth degree Taylor polynomial of f at a, and our limit r sub n of x is equal to 0 where n approaches to infinity, right? So in trying to show that limit r sub n of x is equal to 0 and n approaches to infinity for a specific function f, we usually use the following theorem, that is number 9, Taylor's inequality. Taylor's inequality. If m for absolute value of x minus a is greater than or equal to fn plus 1 prime of x, fn plus 1 prime of x, right, and less than or equal to d, then the remainder r sub n of x of the Taylor series satisfies the inequality. And the formula for that, or we will write in this particular equation, where absolute value of r sub n of x is less than or equal to m divided by n plus 1 factorial, right, and multiplied with absolute value of x minus a power n plus 1. Understand? So what do? We will just, you know, we will add our add 1 in our n value over here in this particular volume, and we'll solve this factorial, and with the help of this equation we'll be approaching, and we'll be knowing to the Taylor's inequality. Understand? So we collect the following table for future reference, like some important Maclaurin series that we have derived in this section. And we can see we have on the left side we have actually the values, and we can see on the right side, the rightmost side, we can see the remainders. Understand? So the remainder for 1 by 1 minus x is 1, right? And for e power x is infinity, sine of x is infinity, cos of x infinity, tan inverse x is 1, right? So natural log of 1 plus x is infinity, and 1 plus x power k is infinity, right? So we have these values. You can just have a reference from these values and the remaining. All right, now talking about the approximating functions by polynomials. Suppose that we have f of x is equal to the sum of the Taylor series, right? And we will just write it down in form of sigma f n of n prime of a by n factorial into x minus a power n, right? The notation Tn, t sub n of x is used to represent the nth partial sum of the series, right? And we can call it as nth degree Taylor polynomial of f at a, as we just discussed in our previous slides, right? So what do? We will just write down t sub n of x is equal to a, and rest we will write sigma f I prime of a divided by I factorial, right? And it will multiply with x minus a power I, and starting I is equal to 0 goes towards r, and because we know that there is a particular number at the end, we will not dealing with the infinity over here because we have to deal with the partial sum of this series, right? So it will be equal to f of a plus f prime of a divided by 1 factorial into x minus a plus f double prime of a divided by 2 factorial minus into x minus a square, right? And it will be going up to f n prime of a divided by n factorial into x minus a power n. So since f is the sum of its Taylor series, we know that t sub n of x goes to f of x, right, as n moves to or tends toward infinity. So t sub n can be used as an approximation of n, and we can say that f of x is approximately equal to t sub n of x. And notice the first degree Taylor polynomial is t1 of x is equal to f of a plus f prime of a into x minus a, and it's the same as the linearization of f at a. Okay, now we have to see one more thing, that t1 and its derivative have the same values at a that f and f derivative have, right? In general, it can be shown that the derivatives of tn at a agree with those of f up to and including derivatives of order n. So we have an example over here to illustrate the idea, and we can see that their y is equal to e power x, and it's the first few Taylor polynomials are shown in this particular figure number 1, right? So you can see y is equal to t1 of x, y is equal to t2 of x, and y is equal to t3 of x, right? And it's going towards like the value y is equal to e power x. So the graph of t1 is here. So the graph of t1 is actually a tangent line. You can see this tangent line over here, and it is at the point 0 1, right? 0 1. So this tangent line is the best linear approximation actually at t1, right? But when we go to our t2, we see there's a parabola forming over here, right? And this parabola is actually having some value, right? We can see the value in the next slide. But when we move to the third value over here, that is t3, it is actually making a cubic curve. You can see this is actually a cubic curve over here, right? So still this cubic curve has a value. Now let's see what are the values of these three things. So the graph of t1 is actually having the value of 0 1 because this tangent line is passing through that particular point. And when we see the graph of t2, it is actually making a parabola and having the value 1 plus x squared by 2, right? And when we talk about the cubic curve, that cubic curve we saw in our last slide, the previous slide, it was having the value of 1 plus x squared by 2 plus x cubed by 6, right? Now which is a closer fit to the exponential curve y is equal to e power x than t2. Now you can see we have been just watching that differentiation, right? Okay, so the next Taylor polynomial t4 would be an even better approximation actually, and then it would be continued. And okay guys, so this is the numerical demonstration of our Taylor's polynomials t sub n of x to the function y is equal to e power x. Now we have three columns over here, right? In the first column we can see the terms of t. In the second column we have the values, right? When we have x is equal to 0.2, and then we have the values when we have x is equal to 3.0. Now you can see when we have x is equal to 0.2, the convergence is rapid, but when x is equal to 3, it is somewhat slower. It is not rapid as compared to x is equal to 0.2, and the values are really different from each other, okay, in the both columns. In fact, the farther x is from 0, the more slowly t sub n of x converges to e power x. So when using a Taylor polynomial t sub n to approximate a function f, we have to ask the questions, how good an approximation is it, and then how large should we take n to be in order to achieve a desired accuracy. To answer these questions, we have to look at the absolute value of the remainder, right? So when we have the remainder, r sub n of x is equal to f of x minus t sub n of x, right? And it would be the absolute values. Both are the absolute values, right? There are three possible methods for estimating the size of. So let's see what are those methods. First one is, if there's a graphing device available, right, we can use the graph r sub n of x and thereby estimate the error. Second is, if the series happens to be an alternating series, we can use the alternating series estimation theorem. And third is, in all cases, we can use Taylor's inequality, which is r sub n of x less than or equal to m by n plus 1 factorial into x minus a power n plus 1. Whenever we have this particular thing, where we have this f n plus 1 prime of x less than or equal to m, right? Okay, now we have an example number 1 over here, and we can find that how we can just apply this Taylor's inequality theorem, right? So guys, first of all, there are two parts, right? First one is approximate the function f of x is equal to x cube root by a Taylor polynomial of degree 2 at a is equal to 8. Second part is, how accurate is this approximation when x is greater than or equal to 7 and less than or equal to 9? So, heading to the solution. For the part 1, we have the solution here, and it's like when we going to evaluate our f of x, right, it would be equal to x power 1 by 3, and when we'll be evaluate our f of a, it would be equal to 2, right? And in the next step, we will be finding the derivative of our f of x and f of a, and the derivative of f of x will be 1 by 3x power 1 minus 2 by 3, and derivative of a, or derivative of 8, would be 1 by 12. Then we will again find the second derivative, right, which would be the second derivative of x would be minus 2 by 9 x power minus 5 by 3, whereas the second derivative of 8 would be minus 1 by 144. Then we'll find the third derivative, which would be, for x it would be 10 by 27x power minus 8 by 3. Thus the second degree Taylor polynomial is t2 of x is equal to f into 8 plus f prime 8 by 1 factorial into x minus 8 plus f double prime of 8 by 2 factorial, actually not second, sorry, 2 factorial into x minus 8 square, right? So this would be actually the second degree Taylor polynomial, and it would be, when we'll simplify it, right, we'll find something like this over here, and the desired approximation is actually cube root x approximately equal to t2 of x, right? So the second part is, the Taylor series is not alternating when x is less than 8, so we cannot use the alternating series estimation theorem in this example, right? what do? We will use a Taylor's inequality. So we have to recall the slide number 14, right? And we understood how we are just going to implement our Taylor's inequality theorem over there. Okay, situation is that our we can see that the value of n is 2, right? And value of a is equal to 8. And now we will just plug in the values over here, and we will write it down in r2 of x less than or equal to m by 3 factorial multiplied with x minus 8 power 3, right? And we can see this 3, it is actually n plus 1. We can see the 3 in as a denominator, 3 factorial over here. We can see the 3, we can see this 3 as a power over here. So these are actually n plus 1, and we have this n2, right? So 2 plus 1 is equal to 3. Because x is greater than or equal to 7, we have x power 8 by 3 greater than or equal to 7 power 8 by 3, right? So the third derivative of f of x would be less than 0.0021. Therefore, we can take m is equal to 0.0021, and also we have x that is greater than or equal to 7 and less than or equal to 9. So it means that x minus 8 would be greater than or equal to minus 1 or less than or equal to plus 1. And we can say that x minus 8, absolute value of x minus 8 is less than or equal to 1, right? So this way we will just plug in the values over here, and we will see that our r2 of x would be less than 0.0004. And we can see this factorial, 3 factorial, we just solved it down, right? And we just find the value of 0.004 over here. Thus, if x is greater than or equal to 7 or less than or equal to 9, the approximation in part A is accurate to within 0.0004. So then we can use a graphing device to check the calculation. Like, we can just cross check, or we can tally your calculations over here, and we can really see that it's closer to these values are really closer to each other when x is near 8. And we can see in the figure 3, which shows that our 2x computed from the expression, and it shows that our 2x is less than 0.003, right? There's a slight difference with the calculation from the computer and with the calculation or estimation with the Taylor's inequality case. There's a very less difference, but still there's a kind of difference in the error, right? So that is all about the approximating functions by polynomials, right? So you have to just carefully go through these examples and these things. Later, if you have any kind of question or any kind of problem, that we can just sort it out, right, in our question and answer session, right? All right, guys, just take care of yourselves, and goodbye till the next lecture.